Okay, so uh, just to introduce myself, I am Zhi Huan. I'm from MIT. I'm now in my third year of PhD, and I'm working with Centil. So today I'm gonna introduce the numerical algorithm called the density matrix renormalization group, or DMRG. Um, Okay, let me start by explaining the plan of my talk. So I'll begin by quickly walking you through this procedure of IDMRG and DMRG. So IDMRG is for infinite DMRG. It's an algorithm working for the infinite size system, and DMRG is defined on the finite size system. So okay, so I'll just without too much explanation, just tell you how the algorithm runs. And then I will take a little bit of digression to talk about the basics of tensor network. And the reason why we do this is in the end, we will come back to explain the DMRG and IDMRG in the matrix product state language. So this is a very helpful way to make things very transparent and obvious to you guys. I also prepared some more applications of using this DMRG, but I don't think today I get time to talk about these. But I will just spend most of the time introducing this matrix product state thing, because this DMRG was invented like 30 or maybe even 40 years ago. But since 20 years back, people have come to know this matrix product state and realize that DMRG actually is based on matrix product state. So now if you look up the literature, recent literatures, people just use matrix product state as a language of describing this algorithms or any new applications of DMRG. I think it's a very powerful tool that is generally helpful. So instead of giving you a detailed description of one or two applications of DMRG, I think it's more important to just introduce this language to you so that you can sit down and figure out other many applications later yourself. Um, Okay, so let's get into the topic. I will introduce the DMRG starting by giving you a little bit motivation. Why? So why do we need a algorithm called DMRG? So we know that as a condensed matter theorists, we are having this generally interested in quantum many-body problems. So there are many interesting phenomena in these kind of systems, such as high TC or spin liquid, like fractional quantum Hall effect, and so on. So, okay, so what comes with this quantum many-body physics is the some internal challenge, which comes from the exponentially growing Hilbert space dimension. As you include more and more degree of freedom into the system, you need exponential large number of parameters to describe the state of many-body wave function. So in classical mechanics, we also have some difficulty related to many-body systems. It's called the many-body dynamics. Right? But here it's another level of difficulty. So we're not talking about any dynamics. We're only talking about describing one single quantum state in the Hilbert space. Right? So classically, if you want to describe a system, you only need a number of parameters growing linearly with the system sizes, right? Like you have a speed and you have position of each particles, right? But in classical mechanics, because of this quantum entanglement, you have exponentially growing parameters to specify a wave function. Okay, so to solve these issues, we have a lot of approaches. Of course, there are analytical approaches, which I'm not going to talk about today, but I will just mention a few numerical approaches. The first is called the exact diagonalization. Basically, that is just to, as the name suggests, you take the Hamiltonian and you do you take the Hamiltonian matrix and you do the diagonalization, right? So if you use this algorithm, you will be restricted to a system size of, I think, no more than 30, yeah, no more than 30 spins. Okay, so on the other side, you have this quantum Monte Carlo algorithm, which is a really powerful algorithm, especially because this algorithm can be coded parallelly. So it means, so as a consequence, it will give you access to very large systems. I think now we can push the limit to 50 by 50. That's 2,500 sizes, sites in the system. So, however, there is another issue that comes with the quantum Monte Carlo that is known as the sign problem, which basically eliminates your, make this eliminates the possibility to attack those problems such as fermions or say frustrated magnets, right? So also notice that yeah, these problems are exactly the kind of the most interesting topics today. So it's almost like a principle that if you want to study interesting things, you always encounter more challenges. Right? So okay, so for these two algorithms, you see they both of them kind of dodges this challenge posed by the exponentially growing Hilbert space dimension. The first one says we just let it grow exponentially, but we have this very small system size, so that is still handleable. And in quantum Monte Carlo, what we do is basically we never really write down a rigorous wave function. What we do is we sample over the path integral in such a smart way, so you still, without writing the wave function, you can still efficiently converge all the physical measurables. You can still extract the observables. Okay, so so the DMRG algorithm works in somewhat a different way. So we really try to settle this issue of Hilbert space dimension growth by saying that okay, the Hilbert space grows exponentially fast. This I cannot do anything about that, right? But what we can do is we can, we usually do not care about entire Hilbert space. Instead, we focus on some low energy state of some special Hamiltonians, right? So if this low energy subspace of the Hamiltonian has some special quality, then maybe I can utilize this special entanglement structure to like minimize the parameter I need to efficiently express the states. So yeah, this is the main idea of the DMRG. Okay, so let me explain the name. We'll see what DM means. DM is density matrix, and here RG means the idea is just to so we cannot directly start with a system with a very large size because the exponentially high Hilbert space dimension, but we can do something just to starting from a simple problem with a small system size, which we can treat exactly, and then we grow up the system little by little. And in this process, we include more and more degree of freedom, and the problem becomes complicated to solve. And so along the way, we just discard the irrelevant information to always keep the Hilbert space we care about always manageable. Okay. So yeah, let me just say what the algorithm does. So first of all, it's called the infinite DMRG. So by the name suggests this algorithm deal with a system of infinite size, but still we grow the system from a very small size. Okay, so you see here the first step, we start with a 6-site system. Right? So each circle means one site. You can put a spin, for example, spin 1/2 here, and you have a local degree of freedom D. So if you have a spin 1/2, then the little d is 2, right? Two-dimensional Hilbert space. Okay. Now, what we do is in this process, this is like one iteration. The whole figure is like one iteration of the IDMRD step. So you see, at the end of the day, we want to grow the system by 2 sites, right? And we want to close this loop and do the iteration. Okay, and you know, as the iteration goes on, in the end, we'll converge to an infinitely long chain. Okay, so let's see what we do exactly step by step. So when we start this algorithm, we divide the system into 2 blocks, called block A and block B. So you know that for the general wave function, the 2 blocks should be entangled, right? So the wave function is something like this. So to write this wave function, we need a d-dimensional basis for each block. Right? So I and j can is summed over from 1 to d. Right? And yeah, so we can write the wave function this way. And then now we can start you know, adding 2 sides in the middle. So we form this block site block structure. Okay. So now using this basis called this block basis, which is the capital D dimensional, and the site base, which is little d dimensional, and this is little d dimensional, this is a capital D dimensional. So you have this, the new wave function written in this fashion. Okay, so well, now we just do the exact diagonalization of this d squared times capital D squared dimensional Hilbert space, right? And we find the wave function. So we basically minimize this object and we find the wave function. Right? Okay, now we want to close the loop by growing the block by 1 side. That means we absorb this side into the block. So, or we just cut the system open again and say we put you know, we combine the 2 what do you call bases into 1 basis, and you see the new basis I prime should take the value from 1 to little d times capital D, right? Okay, so so we can run this you know, we can run this iteratively. Because now we can just go back from the top and do the insert the new sites and do the diagonalization again. But the problem will soon appear, because now you see at the end of this iteration, your block base grow from the capital D dimensional to little d times capital D, right? So here we didn't play any tricks. But you see the Hilbert space dimension. So in the next iteration, the Hilbert space dimension will grow by a default, right? And so soon this problem will be very hard to solve, right? And we don't want that to happen. So we need to do something about it. So what we do is when we include the site, when we do this step and include the site into the block. What we do is we need to do a truncation. So instead of previously, I said keeping D and D states, we always keep capital D states. So we need to discard those degree of freedom that are not so relevant. So there are so many ways the left and right blocks are entangled together, but some of the entangle may be stronger and some may be weaker. Right? So we can just discard the weaker connection between the left and right and only keep the most important ones. And yeah, so that we can more or less express the quantum state, you know, kind of accurate, but still with a reasonable cost of memory. Okay, so
can I just ask a question here? So, you know, if you had asked me to explain RG to someone who didn't know anything about RG, I would have, you know, started from a big system size and then done coarse graining, and, you know, talked about how when you coarse grain, you get to smaller system sizes and non-universal stuff is eliminated, right? But I guess here we're starting from a small size and then trying to grow it, right?
Yeah, it's so, just you see from the you know, the idea of RG is just to include more and more degree of freedom, right? And also you throw away something that's not relevant. Right? So,
well, I guess I would have said the idea of RG is to include like less and less degrees of freedom, right? Like the RG is like integrating out modes step by step, right? So you're slowly getting rid of stuff. you're never
Yeah,
adding
that's
anything.
that.
Right?
I mean, when you integrate out, you're already that's corresponding to my truncation process here. Like
Right. Yeah, I agree.
you're throwing away some degree of freedom, right, by
Right. So
integrating.
what about this? Why do you have to like grow the system from something small? Right.
Because yeah,
Like.
so if you start directly from a very large system size, then you will not be able to,
Mhm.
diagonalize the problem, right? So you have to
Right.
attack the problem little by little, like starting from a
But
simple problem and make it harder a little bit.
so the claim is that even if you're starting with some wave function on a very small system where there are going to be all sorts of like finite size effects and all this crap that
Mm.
is not relevant to the IR solution, right? When you add these
Yeah,
degrees of freedom, they'll all kind of go away.
yeah. So so in the future update, you will throw away these information if they are not relevant in the IR.
I guess just like maybe I would have thought that since you're starting from such a if you're starting from a really small system and you have all this like very very non-universal information there, you might
Mm-hmm.
just be so far away from the fixed point that you want to be that the flow will just be different, right?
Yeah, I
Like
guess the question amounts. Does the
Okay.
question amount to like do errors compound?
Yeah.
Like if you throw away.
Yeah, I think that is right. So it really tells us that this capital G, this capital D cannot be set to be very small, right? So
yeah.
at the very beginning of this IDMRG iteration, you do not really throw away anything because the D this block Hilbert space is very small. You don't need to throw away anything. Right? You can still let it grow exponentially. Right? So maybe once it reaches like 10 sites and you start do the truncation. So how
But
many?
you're are you starting from something that literally only has like 2 sites or something?
Yes, that's right. But the first few steps is not really relevant here because in the first few steps there is no truncation. So we are basically doing the exact diagonalization and we expand the system and we do the exact diagonalization.
But then isn't the statement then that like the Hamiltonian of some system on 2 sites actually contains like universal information about the low energy physics somehow?
No. So as you grow the system maybe to 4 sites, the algorithm is still exact to that point, right? And even to 6 sites because the capital D is so large, the upper bound of D is so large that the system does not really require the upper bound. That does not really,
I see.
The block is still very small that you don't need the upper bound capital D to be imposed.
Oh, so can I equivalently say that the starting point of the algorithm is like some moderately large system, for which exact diagonalization is possible? Okay.
Right. If you consider the truncation process, the beginning of truncation as the starting point of the algorithm, then that's right. So before that, everything is exact.
Okay, makes sense. Got it. Thanks.
Okay.
Great question. So, how is the truncation determined?
Yeah. Okay. I will explain the truncation here, but not in very detail. So, the goal here is I use less basis states here, I prime and J prime, right? But still, I will be able to describe the wave function pretty well. So, what I want to do is to maximize this object. This is the wave function after truncation, and this is the wave function before truncation. So to do this, people find that the best way is to find the reduced density matrix. So this is why it's called DMRG. So just look at the reduced density matrix corresponding to this cut. Okay, basically you trace out the degree of freedom on the right to obtain the reduced density matrix on the left, and you find a matrix, and you can diagonalize the matrix, which is written, gives you the eigenvalue and the eigenvector. Right? So now you pick the eigenvector. And these are just the best basis you would choose to describe the half system. That's the block A prime. Okay, so I'll just, without explaining too much, just give you this result. So here, my purpose is to show you how this works, and we will talk using this matrix product state language. This will become very clear why it is the best way to do the truncation. Okay. Is that okay?
Yeah.
All right. Yeah. Okay. So so let's talk about DMRG. So to do DMRG, we need to first warm up using the infinite DMRG, because still we cannot directly start with a very large system size. Okay, we need to grow from a very small system size and to the size that we want. Okay, so once we reach the size of system here, we end up with this still block side block configuration. And what we want to do is we want to now optimize the system site by site. So we want to optimize the wave function on the different parts of the system. So the way we do this is we first, pick the center two sites and form this kind of full part of the system. And we do the exact diagonalization, and we find the wave function, and just as similar as before, now we want to absorb this site into the right hand side block, right? So what do we do is exactly the same as before. We find the reduced density matrix corresponding to this cut, and trace out the degree of freedom on the left, right? And then we find the eigenvectors on the right. Okay, and using this eigenvectors, I can describe the super block on the right very accurately. And for the left-hand side, we need to, we're basically asking the question, what is the best way? So suppose this block A has length L. Okay, so what is the best way to describe a block A which has a length L-1? Okay, so we have solved this problem in a warm-up step. So we just read this from the memory, right? So here is the L-1 block. So we just read this from the memory. Okay, so in this way, the program can just iteratively be run, and you just sweep the center sites to the left and then to the right, and you just do this back and forth until you reach a convergence in the wave function or the energy. Okay, so this is DMRG. All right.
So does using the smaller size reduced density matrix cause problems, because maybe when you have larger systems you have entanglement between the sides of the system or something? Or
sorry, could you repeat the question?
So there's no problem in for example, like the reduced density matrix for half of the system in a small system, right, is not going to be the same as the reduced density matrix for like a quarter of a system in a bigger system, right? So in this like retrieval step, right, you're borrowing the reduced density matrices you counted for smaller systems.
So this is actually not very careful. So you'll need to be very careful about this, because in the future it will optimize, through this future scan sweep. It will be optimized. So in the future, when you retrieve data, what you retrieve is, for example, you're using the reflection symmetry in the system. Right? So when you sweep from the left to the right, you're doing this. This part of this block is shrinking, right? So this is retrieved from here, right? So even if what you are retrieving from here is not exactly, the 2L length system, right? So it doesn't matter, because you will keep optimizing this basis choice in the future.
I see. So the retrieval is happening at later and later time steps as
yes, it's also happening in the later steps.
Okay, got it. Thanks.
Okay, great. So now to better understand this DMRG and IDMRG and why they work, we will introduce the tensor diagram. It's just a convention or language. So you see here, I draw this little blue dots. That's a tensor, and there is a line coming out of it. that's called index. So here, what you see is a tensor with one index. That is a vector, all right? So there's something we call the bond dimension. Okay, sometimes we call this a leg, or sometimes we call this a bond. Yeah. So we call the thickness of the bond dimension. So that is how many values this index can take. Okay. Okay. So now I see here this is a matrix because it's a tensor with two indices, and also you can have more index that gives you a higher rank tensor. And here we define the tensor contraction. This is when we connect the two lines coming out of two tensors, what we mean is some Einstein summation over the connected indices. Okay, so here in this example, what you see is a tensor with two indices that is a vector contracted with a tensor having one indices. Right? That's a vector. So it's a matrix vector product. Right? Okay. So and in this example, this is two matrices with both indices contracted. So that's a trace of matrix product. Right? You can also easily see here why trace Mn is equal to trace Nm, because the tensor diagram looks exactly the same when we exchange the two. Okay, so now we want to use the tensor diagram to describe what is used for us, that is the wave function. Okay, so for, you see here as an example, we show a wave function for a four-site system. Okay, the reason we choose four-site is because we want to make some connection to the DMRG where we have four parts of the system. Okay, this four-site wave function looks like this. So this is a tensor with four indices. That's just the psi tensor here. Okay. So the alpha, beta, gamma, delta are called the physical indices. And they have bond dimension D, which is the local Hilbert space dimension. If you have spin 1/2, then D equals, the D will be equal to 2. Okay, so that's a general wave function. And we know that we cannot always store a wave function in this form, because as the number of sites grows, you see that the number of tensor elements we will need for this tensor will grow up exponentially. Right? So one may ask, can we just have a tensor network like this? So we just kind of decompose the psi tensor into very small elements, and so they're connected by this called internal entanglement leg. So means these I index are contracted, and J indices, K indices are all contracted. Okay, so suppose we can store the tensor network, store this big tensor for the wave function in this tensor network form. Then it would at least look like that the storage will grow linearly, right, with the system size. Right? If you have more sites, you have more tensors to store. Okay, so turns out this can always be done. So, but that doesn't mean we can store the data at a linear growing cost. Okay, so it is done in the following way. So we can just single out one index and say combine all the three index on the right. So we just see the three indices as one big index, right? So yeah, then this tensor, this psi tensor becomes a matrix because it's a tensor with two indices now, right? And you can use, you can just put any, you can just place any random invertible tensor connecting to the alpha bound, and you're leaving behind something called the V. Using this equation, you can find the V. So the gamma 1 is randomly chosen, is not a unique option. So by doing this, you already single out one tensor, right, on the left, just this part. So you can keep doing this by splitting the beta index out and combining combining it with the internal leg on the left, and then leaving behind the gamma delta. They are the physical degrees of freedom for the next two sites. And now you again do a matrix. You put a random invertible matrix on the second site, and you leave behind something on the third and fourth site. Okay, so by you can keep doing this to end up with this form, right? Okay, so okay, I see here. I also want to mention that the non-uniqueness of this choice of gamma 1 matrix is actually related to this gauging variance of the matrix product state. So okay, so this form is called the matrix product state. All right. So the matrix product state has this gauging variance because we can always insert a pair of tensors in the middle in any bond that are inverse to one another. And then we can just absorb this part into the tensor on the left and absorb this part to the tensor on the right by contracting this bond and this bond. Okay. So in this way, we get a different representation of a matrix product state, but the wave function, the meaning of this matrix product state is still the same. Okay. So this is why it's called the gauging variance. Okay. So we've said that we can always, starting from any wave function psi, and end up with something like this. But that doesn't mean a reduction of memory cost. The reason is you can see the bond dimension here. So once you have many sites and you look at the center of the matrix product state, you find the tensor, the internal bond indices becomes higher. The internal bond dimensions becomes higher and higher. And it's growing exponentially fast. So although you only need to store order n a number of tensors, but each tensor is costing you a lot of an exponentially growing space to store. Right? Okay. So all right, and in the next.
What?
Okay. Yeah. Go on.
Sorry. So why does this gauge invariance help? Like, why don't I just choose gamma 1 to be the identity every time? Or something?
Yeah, you can choose it like that. Yeah. That's fine. That's fine.
But is there like a, sometimes in field theory or something, it's helpful to choose one gauge over another gauge or something. Like,
we will
in
introduce a kind of conventional gauge that would be very useful for the contraction. So to calculate physical measurables, that's called canonical form, right? Yeah, we will get into this later. So yeah, I'm just trying to point out that a matrix product state expressing a certain wave function is not unique. Okay. All right. So we want to later deal with this issue. So clearly, we cannot accept the matrix product state like this. This is not going to be useful for us because of the exponentially growing memory cost. But we will deal with this later. Before doing that, I'm just going to explain how do we use the matrix product state to extract something meaningful. For example, this is very simple. So we want to find the overlap of two matrix product states. Right? So what we do is we take the bra state and the cat state, and we want to sum over the physical indices, right? So in the tensor network language, we just connect the physical bonds right, between them. And we do the contraction of this tensor network. We do this in the following way. We first maybe say contract this bond and make this a bigger tensor. And then we contract this bond and to absorb this tensor. Right? So this is the new tensor and the second step. And then we contract this bond and this bond to make it an even bigger tensor. Okay. So we can keep doing the contraction. You're just absorbing one tensor at a time. Right? Okay. So in the end, after the entire tensor network is contracted, you end up with the complex number, which is just the internal product. Okay. And similarly for expectation values of some local measurables, we just put some tensor in between the bra and cat, and you see the SZ is just the Pauli matrix, and So it is a matrix. So it has two indices, sigma and sigma prime, connecting to the bra and cat space, right? Each bond is two-dimensional. So you just again contract this tensor network, and you get the expectation value of SZ. Okay. All right. So okay, back to the previous question. How do we compress a matrix product state with bond dimension that is very high, higher than what we want? So into capital D dimension, and with minimal loss of fidelity. By fidelity, I mean the inner product between psi and psi tilde. That's the psi tilde is the wave function after the compression, and the psi is the wave function before the compression. Okay, so we want to do something like this, making the bond dimension small enough so that we can deal with this matrix product state. Okay. Okay, so here I will show you an example about a two-side system whose wave function is like this way. And okay, so I can have a way to write down the wave function using this matrix product state. So let me show you how I do that. This is not the smartest way, but that's one way to do so. Then I will show you how to improve this expression to make the space caused by the expression smaller. Okay. So what we do is now we notice there are four ways the system, the left and right subsystem are entangled together, right? So we have this leg called the internal entanglement bond, right? That basically, because in the end, the wave function looks like this, and we are summing over the J index, right? So we can say, let's assign each term or each way of entanglement between the two parts to one index of J. So for example, if we take J equals 1, the J equals 1 will, in this expression, will give the first term. Okay, and J equals 2 will give the second term. Okay, so let's look at the expression here. So this is when J equals 1. Okay, so in J equals 1, what I want is when alpha and beta equals 0, I should get something. The product should be 1/2. Right? So I just assign it symmetrically, 1 over square root 2. And all other index should be 0. All other tensor elements should be 0, right? Because for the first term, I only have 0, 0 component that is non-zero. Okay. Then also similarly for the second term, so I will use J equals 2 to take care of the second term. Right? So J equals 2 here, and I want alpha equals 0 and beta equals 1 to give me a wave function that's minus 1/2, right? So I just assign this 1 over square root 2 and minus 1 over square root 2 to the two tensor elements, right? And all other elements are 0. Okay, so I can do this for all four terms, and yeah, in the end, I end up with a tensor network, a matrix product state, which has an internal bond dimension, D equals 4, right? D prime equals 4. Right? So we have J equals 1, 2, 3, 4. Okay, so the gamma is a 2x4 matrix, basically. All right. Now, some of you may have already noticed that this wave function can be written in a very simple way. So this wave function is actually not entangled. Right? So if you write it in the x basis, so quantization axis to be, you choose to be x. Okay, then you find the state is just a product, a direct product state. Okay, so now you write down, when you write down the tensor network, you will only need one internal bond dimension, right? So because there is only one way of entangling the two parts of the system. Okay, so you can assign the tensor elements in this way that will give you the wave function you want. Okay, so in this process, we choose a smart way to choose a smart. We made a smart choice of local basis so that we can express the wave function with a less memory cost, right? Okay. All right. So previously I just said something a very special example, but now I'm gonna give you a general way to find this good basis. So what we do is the following. So okay, suppose we start with okay. Again, we look at the four-site system, right? But it's not important. We can also start with just a two-site wave function. So we can convert the four-site system to a two-site system by combining indices together. Right? So the reason I draw a four-site system here is just to trying to make connection to the MRG again. Okay, so you can just start by looking at this tensor. Okay, this is a tensor that describes, so here we basically contract this J bond and combine the two indices to form a bigger index. Okay, that's physical, and this is internal and contracted. So here we have basically a matrix, right, with two physical indices. Okay, so the wave function looks like this. All right. Now what we do is, in quantum mechanics, known as Schmidt decomposition, and in the tensor network language, it is corresponding to a linear algebra operation called singular value decomposition. So let me remind you what the SVD does. It does the following. So you start with some tensor, a matrix, gamma L, gamma R. So let's assume the bond, the physical bond dimension here is M and this bond is N, okay? So this is an M by N matrix, okay? So by doing the SVD, you split this matrix into this form. So here it's a S, the S is a unitary matrix, which has its column vectors orthogonal to each other. And the lambda is a diagonal matrix, and the diagonal values are real. So U dagger here is also a unitary matrix, and it has its row vectors orthogonal to each other. Okay, so in the tensor network language, we'll write it like this way. So here we use a triangular to represent the fact that the S has column vectors orthogonal to each other. Okay, so all right, so now we have written the wave function in this form, and so notice that previously I said this orthogonal condition between the column vectors of a S matrix, it can be converted to this form in the tensor network language, because this is basically a product between S dagger and S, and that should give you an identity, right? So it's delta ij. So delta ij is in tensor network language just a line connecting the two indices, right? Okay, so this will be very helpful in later. So now we just use the fact that the lambda tensor is diagonal, and we can write down the wave function in this way. So this is the familiar Schmidt decomposition. Yeah, okay. So, all right, with this, we can think about how to compress the matrix product state. Okay, so just a reminder, we want to, the ultimate purpose we want to achieve is to maximize this internal product between the state before and after a compression, right? So we just write down this expression using tensor network language, okay? So this is the S tilde, lambda tilde, U tilde is something that is truncated, okay? So, so we see from this picture, because we are using the property here, this one, so the two triangular tensor can be replaced by a directly connected line, right? So we are replacing this tensor network in this form. So now you see what is this internal product. This is nothing but the product of the Schmidt values, right? And sum over I, right? Okay, so now we know what is the best way to compress the MPS and while preserving the maximal overlap. That is to choose the the leading leading Schmidt values in this SVD decomposition and keep them and discard the rest, right? This is the best way to go. So, so the truncation is done in the following way. Here, basically, I'm discarding the small diagonal elements and also the corresponding eigenvectors, right? Row and column vectors, and keeping the most important eigenvectors and eigenvalues. Okay.
Okay. So how do you? So let me see if I understand. Like you choose some value of D, and then you maximize. Like you pick the D largest eigenvalues.
Right. So D is previously chosen, fixed throughout this algorithm.
It's kept fixed throughout the algorithm.
Yes.
And
So
is that like something?
Keep a D-dimensional Hilbert space, right? So I always keep the basis to describe half of the system. Right?
Yes.
So once I notice the bond dimension grows beyond D, I want to do this truncation. And what I do, keep the Schmidt values.
And like my question is this controlled, or is this like a parameter that like you choose, and like how should I, for example,
yeah, I think close to the end of the talk, I will mention that. But usually you just choose like order of 1,000. Just choose the maximal value that your computer can deal with.
Okay.
Previously we said that you want, in the end, you want to diagonalize the Hamiltonian of this dimension, right?
Okay.
D squared by capital D squared, right? You don't want this to be very large that can take you forever to do the diagonalization process. So you always set the value D that is reasonable. Okay.
So D is like a function of like the computer that you're doing this on, basically.
Yeah, maybe.
Where you can manage.
If you want to achieve the best accuracy, that's what to do.
Okay. All right. Thank you.
Are there like math results that tell you like how you would expect this like a lambda squared thing to fall off as for like very large in the limit of large?
Oh, yeah. There are. So it depends on the system. Okay. In the end, I'll also say a few words on that. So usually it decays as a power law for the gapped system. Yeah, in one dimension.
Power law for the gaps.
Yes, and in 2 dimension, it decays slower. Yeah, I'll mention that in the, by the end of the talk.
It decays slower than a power law, or a slowing power law?
I don't know exactly how it decays, but you can think about going from 1D to 2D by stacking the chains together. Just coupling a bunch of one-dimensional chains together, and you can observe the decaying power of this of this behavior of the lambda alpha over alpha, right? And you will see the power will go down. The power will go down. I think it's 1 over width. W is the width of this.
Got it.
All right, let's go ahead. Okay, so yeah, so here you basically have seen the something very similar to the previously what I mentioned as the truncation process, right? So here I'm just basically showing you choosing the leading capital D number of Schmidt values will give you the best efficiency in terms of compressing the matrix product state. And now I want to really make connection to this density matrix renormalization group. So there, when we do the truncation, we look at the reduced density matrix, right? In fact, these give you the same result. So previously we said we just diagonalize the reduced density matrix, find its eigenvalues, right? And the corresponding eigenvectors, and use its eigenvectors as the basis for the half of this system, right? So here, what we do is we look at so we put the matrix product state into this SVD form, and then we look at the reduced density matrix, okay? Now, what is the reduced density matrix? We basically trace out the physical degree of freedom on the right to obtain the reduced density matrix for the left half of the system, okay? So by doing this, again, notice that this is UU dagger. So that gives you a delta J prime, right? If it's J and J prime. So, so the reduced density matrix is really something like this, okay? So yeah, so basically when you do the SVD, you basically diagonalize the reduced density matrix. Okay? So S is the eigenvector, and lambda square is basically rho. Yeah. So lambda I square is rho I. So when you pick the largest the dominating eigenvectors corresponding to the largest eigenvalues of the reduced density matrix, you're basically choosing the eigenvectors corresponding to the Schmidt vectors corresponding to the largest Schmidt values. Okay, so yeah, basically it's saying that when I do the SVD, I'm just doing the truncation process in the DMRG. Okay. So yeah. So here I will. Okay.
Can I ask? Maybe this is jumping ahead, but I'm trying to understand how keeping the largest Schmidt eigenvalues is the same as like getting rid of short range entanglement or stuff that people say, right? So, can I say that throwing away the, since if I am computing the entanglement entropy of if I'm computing the entanglement entropy, then I'm taking sums of logs of these Schmidt eigenvalues, right?
Mm-hmm. Yeah.
So if we think about getting rid of the like short, people tell me that the DMRG is supposed to be like getting rid of short range entanglement, right? So is that the same as getting rid of these small Schmidt eigenvalues? How to say that?
Yeah, probably. I'm not sure about that. I don't know how to see whether it's short range or long range. I'm just, I think here is we are just getting rid of this, weak entanglement.
Yeah, I guess it seems to me like this procedure is.
Yeah, I think usually maybe the short range entanglement are the weaker ones, because for long range, when you do a cut to the system, if there is long range entanglement, then you will observe a lot of entanglement between the two sides, right? But for short range, it's usually a very weak entanglement. Right? Does that sound
right? So, but okay, so I would get high entanglement if like the Schmidt eigenvalues were kind of like more uniform, right?
Right. Yeah, if it decays slowly, then that means the entanglement in the system is strong.
Right. So somehow the okay, I guess I'm just curious about like you. It seems like you're keeping the fact that you're keeping large Schmidt eigenvalues might mean that you're just keeping like entanglement coming from the cut between the left and right parts of the system that you made. Mm-hmm. Like this procedure of focusing on reduced density matrix seems like it emphasizes like the local short range entanglement at the cut site or something.
Is that necessarily local? I don't know. Yeah. Yeah, I'm not sure about this.
Okay, well, I mean, let me think about how to exactly say things. More things.
Okay. Okay, so yeah, let me go on. We have talked about, we have explained how you can reduce general wave function into a matrix product state, right? And now we also explained how to compress the matrix product state into the upper bound. So into a, to restrict the bond dimension to below capital D. Okay, so we just now combine the two processes, and we can just start from any random state and arrive at a matrix product state like this, which is what our computer can deal with, because the bond dimension is finite, and the memory cost of this matrix product state will grow up linearly with the system size. Okay, so this structure is called actually canonical form. So in fact, this is called the left canonical form because all the tensors to the left are in this unitary triangular tensor, and this one can be anything. And also you can have other canonical form called the mixed canonical form or right canonical form. You do this by shifting the, this is what we call a gauging center, canonical center, I don't know. But we just shift this, this circle tensor to the left. Okay, we do this by in the following way. So we just contract this bond and make this a big tensor. And we do SVD to this big tensor and split it into 3 parts. And now we find this part is good because this is already in a unitary matrix. And we want to combine this two to become this circle tensor. So by doing this, we have shifted the gauging center from the right a little bit to the left. And we can keep doing this to move the gauging center anywhere we want. Okay, the reason we define this canonical form is because, of course, it's very useful. So for example, let's compare. So previously we talked about how to extract the local observables, expectation values, right? So suppose, so to do this contraction, we need to do it site by site, right? We need to first contract this 2 tensors and then contract this big tensor with the tensor next to it and go on. And so for when a system is very large, it can take a very long time to do so. So what if I can put this matrix product state into this canonical form? Then the contraction will be very simple because we immediately identify that this structure gives me just a directly connected line here, right? And we can reduce this also to a connected line and make this a connected line. So in the end, we just need to contract between the local tensors and the local operators. Okay, so yeah, that's a benefit of a canonical form.
Wait, but doesn't if I'm interested in the site, this SZ on one site, I mean, isn't it hard to do the basis change so that I get into canonical form for that site?
It is. But suppose, when you measure the correlation functions, you need to do a lot of measurements, right? So you need to do a lot of, you need to calculate a lot of SZ expectation values. So so you just do the canonical transform at the very beginning, and then all the contraction later will become a lot easier. That saves you from, because if you consider it's an infinitely long chain, right? So you only need to do the SVD transform at the first step, and then all the contraction that calculates SI and SJ for all the IJ will become much easier later.
I see. So this nice form is preserved by adding in, is preserved under the adding in sites step.
Yes. We'll see how do we, in fact, in DMRG, in IDMRG, what we generate in the end is naturally the canonical form. Right? When we insert 2 sites and we do the, the truncation process, what we naturally obtain is just the canonical form. Yeah, we'll show this later. Yeah. Okay, so before really going back to the DM, I'm going over time. Sorry. So let's finish this quickly.
But you still have 33 slides left.
No, I'm not intended to finish all of them. So that's fine. That's fine. So we have we need to define what is the matrix product operator. So for an operator, it's also can written in this tensor product form. So the Hamiltonian, for example, here is a Heisenberg Hamiltonian. And in Heisenberg Hamiltonian, we have 3 terms, Sx, Sx, Sy, Sy, and Sc, Sc, right? So we just assign the 3 terms to the 3 indices. So the dimension of bond dimension of this iodine index is 3. Right? So we write the tensor elements like this, and then we just this tensor network will give us an operator like this. Okay. Yeah. All right. So finally, we can talk about the DMRG in the MPS language. Okay. Suppose we look at starting from this step. We're starting from a tensor network like this. Okay. Let's see what we do in the following iterations. So first, yeah, the wave function is like this, and we want to ask, what do we put in the middle? Like what object is in the middle? And we do this by minimizing the Hamiltonian, the energy, right? So basically, we're dealing with this tensor network, which is the expectation value of the Hamiltonian. The middle layer is the Hamiltonian MPO, right? So this is bra and cat. Okay. Now we are only optimizing the middle part of this tensor network, and these these blue parts are fixed. Okay. So that means we can just contract all of the object inside and make it a bigger tensor called the effective Hamiltonian for the two sides. Now we find the problem is reduced to so these bonds are having its bond dimension labeled here. So you find if you just combine all these 4 bonds together to be a thicker bond, then the psi is just a vector, and the H effective is a matrix of this dimension. Right? So you are just diagonalizing the H effective to find the psi vector. Okay. Then we find the psi tensor, and now we do the truncation by doing the singular value decomposition. Okay. So by doing so, we get, so this bond is dimensional, d-dimensional, and this bond is little d-dimensional. And after an SVD, what we get is the intermediate bond is this dimension, and this is too high. So we want to do the truncation. So yeah, basically we just discard some of the Schmidt values here in the lambda tensor, and we keep only the largest of them. And then we can grow the right block by one side, just to include this yellow triangular tensor to the right. Okay, and now it's also obvious what we do for the left. We just pull one triangular tensor out of the left block, and now we want to go to the next step of iteration that is here. So we want to ask what is the tensor that we should put on these 2 sides. Right? So this is just one step of the sweep. Right. So now I'll explain the IDMRG in MPS. So what we do is every time we end up with this form, and we include 2 sides, 2 physical bonds in the middle, and we get we want to ask what the tensor is, and we do this also using the diagonalization of Hamiltonian matrix, just as it's very similar to the finite DMRG problem. And after this, we just do a singular value decomposition and make it into 3 pieces, and you absorb the tensor, the triangular tensor to the left and right to form a new block basis. And you can go to the next round of iteration. All right. So, all right. So in the end, I'm gonna show you how we usually assess the convergence of the DMRG result. So this is a benchmark for like a spin 1/2 system, spin 1/2 Heisenberg Hamiltonian, which is exactly solvable. This is on the left, you have a result of energy convergence for finite DMRG. On the right, it's infinite DMRG. So here they use bond dimension M instead of the capital D I use. So in this plot, the bond dimension M is like 20. And you see when you sweep in finite DMRG, you sweep across the system back and forth. and you see the energy just converge to some value. And this, the accuracy is given controlled by this bond dimension, right? Just like here. Okay. So yeah, usually m equals 100 is very poor accuracy. So usually you want 1,000 bond dimension, even for a one-dimensional problem.
When I'm looking at this plot on the right, I notice that m equals 50. There's this weird, maybe it's just an artifact of the plot.
Sometimes there is some oscillation that can happen, because every time you don't always reduce the energy, I think, because every time you introduce some, you mess up the state a little bit by doing the truncation, right?
Right.
So that doesn't necessarily always go down the energy. Okay, so we have two other criteria for the reliability of the DMRG result. One is called truncation error. That is, so the Schmidt values decays, right? Schmidt value decays versus the ranking of them. So we do a truncation here, say this is 1,000, and we are keeping those and discarding those, right? So we want to know how much weight we are losing from this truncation, right? So that's given by this. That's basically telling you how much the loss of fidelity is in this truncation. And the other criteria is called cutoff, which is basically given by the largest Schmidt value that you are discarding. Okay, usually I think 10 to the minus 8 will be a reasonable cutoff that's acceptable. Okay, so all right. In the end, I will comment on why the DMRG works and why it fails. So people have did a lot of work to understand why it works. So they look at the decay of Schmidt values. So they find for the 1D gap systems, it's a power law decay. Yeah, like I said before, so if you include more and more 1D chains to form a quasi 2D system, so the chain is infinitely long, but there is a finite width on this direction. Then you find the decaying power drops. Yeah, so as 1 over W. Yeah, so once you get to the real 2D system, basically it doesn't decay as a power law, I guess. All right, so the other argument about why DMRG works is just to look at the, instead of looking at the whole spectrum of Schmidt value, we just look at the entanglement entropy, right? So we know that for MPS with bond dimension D, the maximal entanglement entropy it can give is log D, because the maximal entanglement entropy is basically when every Schmidt values are equal, right? So you calculate the entropy that is something like this, which is log D. Okay, so on the other side, you can we also have this very nice area law, which states that for any local gapped Hamiltonian, basically the picture is that you only have this very short range entanglement, so that for any partition, you want to look at what's the entanglement between the green part and the exterior, the blue parts, and the entanglement entropy should grow proportional to the circumference of this the region, the green region. So it's called area law. Basically, S proportional to L to the D minus 1, where D is the spatial dimension of the system. And that means
so sorry. So this is the area law is consistent with the fact that the Schmidt eigenvalues are asymptotically constant in 2 dimensions because of some like order of limits or something here. Like why, having lambda alpha be a constant would mean the reduced density matrix is as entangled as it could possibly be, right? Which is definitely not area law.
sorry, could you repeat that?
Yeah. So let's see. So you said quasi 2D, right?
Mm-hmm.
This C is going to 0, right?
Right.
Like lambda alpha is becoming a constant. Well, if I say that lambda alpha is becoming a constant, then
so I think this is basically a very rough estimation, which probably just work for very small widths. I'm not sure if you get a width very large, what will happen. Does
it become some sort of logarithmic decay instead? Like in a true TB system, would it be like a logarithmic type decay instead of a power law? I'm just thinking like the exponent goes to 0 and then.
I don't know if that gives you. If you had the Schmidt values going as a logarithm, that doesn't seem. It would seem to me that they would have to go to 0 faster if you wanted. I mean, having s go as L to the d minus 1, right? If is essentially s being equal to 0 when you take. It's L to the d minus 1 is 0 compared to L to the d, right? So it would seem like to me, I would have thought that the Schmidt eigenvalues should actually decay faster or something, because there's like sort of less entanglement in a gapped system in 2 dimensions than there is in 1 dimension, sort of. I don't know, but maybe it's some subtle thing about like how you're taking the thermodynamic limit and how exactly this. As Johan was saying, how exactly this thing is decaying.
I'm not sure I understand that. Why the entanglement entropy? Why the Schmidt value should decay faster? I think in 2D the entanglement entropy is higher than in 1D, right? Is that not correct?
Yeah. Well, I'm just saying. So if you had like the biggest possible entanglement entropy that you could possibly have would be like a volume law, right? And if it was a volume law, then for example, you could take the reduced density matrix to just be the identity, right? And then in that case, all of the lambda alphas would be the same, right?
Mm-hmm.
So having all the lambda alphas be the same is like area law, right? Yeah. So this
it's lower. So I mean, compared to the volume law, it does decay faster, right?
Yeah. It's just you can't have constant Schmidt eigenvalues, right? If you had constant Schmidt eigenvalues, then you had a volume law. So they have to decay in some form. And if I literally say C is 0 and they're not decaying, maybe it's this logarithm.
Okay. So I think maybe C equals 0 will give you some other decay pattern. That's just not power law, but it still decays, right?
I think that's kind of what Seth was saying. Yeah.
Okay, I see. Yeah. All right. So according to all error law, the entanglement entropy in one-dimensional gap system will be a constant, right? So that means as long as we have large enough D, we should be able to handle this, handle the entanglement, and the challenge will not grow as we scale up the system. Okay. But however, in 2D, this doesn't work because as systems grow larger, the entanglement entropy is growing. So at some point, this will be smaller than the real entanglement entropy. Right? Okay. So yeah, this is basically what I'm going to talk about today. So the picture is just like with a large enough bond dimension, you can get access to the entire Hilbert space. But when you restrict yourself to a smaller and smaller direction, you're focusing on a very small corner of the entire Hilbert space. Right? But the good thing is for the class of model we're interested in, the low energy Hilbert space happen to lie in this small corner. Right? So that is why the DMRG works sometimes. So yeah, I've gone over time for 20 minutes. Sorry about that. I should probably stop here.
That's okay. It was very interesting to me. Great talk. Thank you. So is there, I guess the title of your slide is prompting me to ask this, but is there a case where DMRG like notably fails? Like,
sorry, DMRG what?
Like, is there like a canonical example for the failure of DMRG? Like somehow this low energy Hilbert space.
It's very easy to find. You can find any two-dimensional system and it just doesn't work.
Okay, got it.
Okay, and also just to say this, in 1D, if you look at the critical case, the entanglement entropy is scaling very slowly with L, right? So usually we still believe this is treatable. This issue is, these kind of problems are treatable by DMRG. But if you use infinite DMRG, you should be careful that there is an issue that entanglement entropy is growing, because infinite DMRG have a very large system size, and even a slow growth can exceed this limit. Okay. Yeah, but for 2D system, it's even the local gap, the Hamiltonians will not, you cannot use DMRG for that.
So what percentage of people who haven't been doing DMRG for like their whole lives or whatever use 10 pi now?
And that's very easy to use. So as long as you understand the tensor diagram language, yeah, the code is very easy to read. And the documentation is also written all in the tensor MPS language. So yeah, I guess it's really not that hard.
Yeah. So there's really no reason not to, if you want to like play around with, or do something like the first time, there's no reason not to do that. Right?
You can just write the DMRG code with like 100 lines. You don't really need to code that much. So the main algorithm is just a one-line code. So, and you can read the online documentation about how the more advanced applications works. Like I think at least they mentioned the quantum numbers and the correlation functions, yeah, and so on. Right.
Oh yeah, and so I guess maybe this is obvious, but the criterion we were using when doing RG was the fidelity of the wave function, right? Or fidelity of the reduced density matrix.
Yes.
So is it true that like if you have some bound on the fidelity, then that implies some constraint on like correlation functions of local operators or something?
Sorry, what do you mean down on the?
Like if you know that I'm using this wave function overlap, right? So if I know that my wave function overlap differs from 1 by epsilon, right? Does that mean that when I compute correlation functions of local operators, then the error that I get in those correlation functions will also be like appropriately small in epsilon or something?
Yeah,
I guess
relation. I mean the direct connection with the truncation error to the property of the wave function is through this entanglement, right? So, the higher the truncation error, the more entangled the system is, right? And yeah, I'm not sure if how is the connection directly between the the correlation functions and the entanglement. Yeah, I think there's probably some connections there. Yeah.
But so no one ever uses any kind of other metric other than the wave function overlap to assess like how accurate they're being. Like there's no better diagnostic than that, right?
I think you can also measure the correlation length, right?
Okay.
Right. So usually a longer correlation length means you are describing the system quite faithfully.
Right.
When we solve practical systems, is there like any advantage that we use DMRG or IDMRG to the one?
Oh, okay, so there are those examples that you want to get rid of the boundaries. I think maybe symmetry protected topological spaces, where the gapless degree of freedoms sits on the boundary. And if you want to only look at the bulk properties, then it's a good choice to use IDMRG, and the convergence, at least for some problems, turn out to be many times higher. I think an order of magnitude higher. Because the bulk is gapped, right? And the boundary is, it's usually easier to, do exact diagonalization for Hamiltonian that is gapped, right? Right. Yeah, any other questions?
If not, we can thank you, Jiwon. That was a really good talk. Cool. Thank you guys for coming. Next week will probably be an hour later, but I'll send out everything on Slack and via email.
Gives me 1 more hour to prepare. Nice.
You're welcome.